Permutations with groupings. I had restrictions there, but I think it's easier if we just remember this as permutations with groupings. And this is the idea of you want to arrange things, but you want to keep certain things grouped together. And the strategy is count how many groups you have, arrange your groups first, then look inside each group and arrange how many ways you can do things inside each group. So we'll start with an example to sort of explain this. Here's my example. I have got, you need these notes? I have got a bunch of calculus, a whole bunch of math books. And I want to arrange them on a shelf. But I want to keep the subject areas together. So my first decision that I have to make, decision we put spaces, first decision I have to make is, well, should I put calculus first, then algebra, then geometry, or should I put my algebra books first, then geometry, then calculus? So my first decision is arranging my groups. And I have 3 groups. How many choices do I have for arranging 3 groups? 3 factorial. Then after I've decided, okay, I'm going calculus first, then algebra, then geometry, now I look within each group. Once I look in my calculus books, well, I have 4 of them, assuming they're all different. They're not identical objects here. 4 different calculus books could be arranged in 4 factorial ways. 5 different algebra books could be arranged in 5 factorial ways. And 4 different geometry books could be arranged in 4 factorial ways. So it is a spaces question. We have 4 decisions we need to make. Inside that, we have lots of choices. And with a decisions question, we would take all of this, put it into a calculator, and multiply it all together. So you can test that if you've got your skills with check your skills out with your calculator. You should get 414,720. 414,720. So we're going to use the grouping strategy whenever things need to stay together inside of larger permutations. So sometimes we get these grouping strategies like this. We have 5 people that want to sit on a park bench. Amy, Bill, Jill, Lee, and Tom. In how many ways can they be seated if, Jill and Bill want to sit together? Isn't that nice? So if I draw a diagram, Jill and Bill are going to get grouped together. And we still have Amy, Lee, and Tom. This is a grouping question. As soon as something needs to stay together, we have a grouping question. And grouping questions, we always start off by arranging the groups. Now, this is sometimes tricky. How many groups are there? 4. Can you see yourself thinking 2? But do these 3 have to sit together, Amy, Lee, and Tom, or could they be, like Jill and Bill could be in between them, right? So there are actually 1, and then these are singles, but they're groups on their own, 4 groups. Sometimes this is easier to think about if you think about now. I don't know if you've ever seen couples that once they start dating, they are never apart. It's like everywhere you go, you see them together. I mean, when I was in high school, we just changed their names. We just instead of Jill and Bill, we just started calling them one thing, the Jill Bill. Oh, there goes the Jill Bill. because they're one person now. They do not, you never see them apart. They're like glued together. And so when you're thinking about the groups, sometimes people think of this as like, well, now there's just 4 people on the bench. There's the Jill, Bill, Amy, Lee, and Tom. 4 factorial ways you could arrange them. But in a grouping question, the next decision you look at is how many ways can each of the groups be arranged? And the Jill, Bill, they could be holding right hand, left hand, or they could be holding left hand, right hand. There's actually 2 factorial ways of rearranging the Jill, Bill. Amy, Lee, and Tom, you could draw spaces for them and put 1 factorials in there, right? I wouldn't, but if you wanted to, Amy, Lee, I'll do it in a different color. You can put 1 it's like multiplying by 1. It's not going to make a difference to your answer, right? So I multiply this out and I get, there are 48 ways that they could sit on the bench and Jill and Bill are sitting together. Part B. Uh-oh. Now, Lee and Amy also want to sit together. Laney. Poor Tom. Don't worry, he gets his revenge in part 3. We'll see that later. But now we've got Jill, Bill together, Lee and Amy together, and Tom. Now how many ways can they sit on the bench? Well, we always do in a grouping question. We look at the number of groups first. And now there are 3 groups. So 3 factorial. 2 of those groups have more than 1. There's the Jill, Bill group. And there's the Lamey group. I mean, technically, if you wanted to put Tom, you could, but you don't need to. We multiply this together, 2 times 2 times 6, we get 24 ways. And then part C. I'm just going to, I know I have it written down there for you. I'm going to just erase this part. Just to talk about it. Something happens, and now Jill and Bill must not sit. It's amazing they still go to the park bench. Okay? And Amy and Lee in part C, they're kind of like, they're not that couple that's always together. They could sit together, but they don't have to. But we just need to make sure that Jill and Bill do not sit together. This is a perfect example of where the not strategy comes into play. Sometimes it's a lot easier to count what should not happen than what should happen. And remember, the not strategy is always all minus the bad ones. All of them is just all the ways 5 people can sit on a bench, which is just 5 factorial. No other restrictions. Subtracting the bad ones, well, the bad ones we counted in part A. There was 48, right? The bad ones would be Jill and Bill together. We did that in part A. We counted 48 of them. If we take the 120 and minus the 48, we're going to get the 72 ways that they're not together. And this kind of leads into our last strategy, because the other way of doing this is called cases. And in this example, the cases would be quite complicated. Here's my 5 spots, right? Jill and Bill can't sit together. Is it possible Jill could sit here? Yes. If Jill sits there, this one has a restriction. It's not Bill. How many people can sit there then? How many choices do I have? Three, because Jill's already here. Now there's no restrictions left, and this would be 3, 2, 1. If Jill is on the end and not sitting beside Bill, there's going to be 18 ways. Next, it could be possible that Jill was there. Do we have any restrictions? This is not Bill. This is not Bill. How many choices do I have here? 3. How many choices do I have? Well, this is 1 because Jill is there. How many choices do you have here? 2. How many left? 2 and 1. This will be 12 ways. We would list this as case 1, case 2. How many cases am I going to have in the end? Jill here, 3. Jill here, 4. Jill here, 5. And then if we count all of those cases separately and add them up, I'll tell you it's going to add up to 72. Yes?
How are you getting 18 and 12?
3 times 3 is 9.
Oh, you're
Times 2,
multiplying?
it's decisions. We always, with spaces and decisions, we multiply.
Or
Right? Jill here. Not Bill here. Not Bill here. 12. Jill there will be another 12. Jill here will be another 18. Add those all up, you'll get 72 as well. But you see that this is a place where that not strategy is a lot easier. Okay? But we're going to get some places where we have to count things in cases. And this is the last permutation strategy that we're going to learn before going on to combinations. So if you cannot count things all together, you break them up into separate little things that you could count, just like Jill and Bill. We could have thought through every situation where Jill could sit and count those and then add them all up. That's the idea of cases. And the way that we show our work is when we're doing this, we break it up and write out case 1 and explain it. This is going to be a cases question because of the wording right here where it says at most 3 different digits. So we have to count the 3 digits, the 2 digits, and the 1 digit separately. 3 digits, there would be 3 decisions. Do we have any restrictions? How many choices do you have for the first digit? 10? If you start with a 0, it's a 2-digit number. So there is a restriction that this is not 0. So there's only 9 choices there. And then 0 could be put back in. But since they have to be different, you've used up a number, there's only 9 left. And then 8. For 648 total. Case 2. 2-digit numbers. 2 spaces. Again, there is a restriction here that this is not 0. 9 choices. Now 0 could be put back in, but one of the numbers is gone. 9 choices again, giving us 81. And then case 3, 1-digit number. Is 0 a number, a single-digit number?
yes.
Yes, it is. So now we can put all 10 in here. And then you add up your cases for 739 total. Okay. Another place that you get a cases question is when you have a decisions question or a spaces question where there's more than one restriction and those restrictions overlap. So here we're using the numbers 1, 2, 3, 4, and 5. No repetition is allowed. We need to make a number greater than 300 and even. So when I draw my spaces out, and don't write this out, I'll do it in red. This is not going to work for us. Right? Greater than 300 means there's a restriction. What are my possibilities for the first one? Either a 3, a 4, or a 5, right? I also have a restriction on my last digit. If it's going to be even, this is a 2 or a 4. Why is this strategy not work? How many choices do I have? 3. Deal with restrictions first, right? How many choices do I have? 2. How many numbers do I have left after I've used up 2 numbers? 3. Why is this not right? Why is 18 bad as an answer? Okay. So let's review. Let's just rewind a little bit here. When I deal with this restriction first and I put 3 choices, I could have picked a 3. If I picked a 3, I would still have 2 choices left. But what if I picked the 4? If I pick the 4, then I can only do a 2 here. So the problem here is I don't know if I should write a 1 there or a 2 there. It's a problem. Because if I pick the 4, I can't put 2 anymore. But I don't know which one I picked because I just said 3 choices. So we run into a problem that way. And the problem is because we have an overlap in our restrictions. That 4 could be in both places. So the way that we solve that problem is with cases. And we take one of our restrictions. I'm going to take the last one because there's only 2 choices and split it up. I'm going to say, well, first I'm going to count all the ones that end with a 2. So I took my last restriction and now I'm saying it has to be a 2. Then when I look at my first restriction, can you see that all 3 of them, the 3, the 4, and the 5 are possible? 3 choices there. How many numbers are left? We chose the 2 there. We picked one of the numbers here. We've used up 2 numbers. We would have, of the 5, 3 choices left for 9 in total. Case 2. What didn't we count? We didn't count all the numbers that ended with a 4. So I do my 3 spaces, and now I'm saying this is a 4. 1 choice there. But now my first restriction leaves me only with a 3 or a 5. 2 choices there. No restrictions left in the middle. 2 times 3. 6 total. 15. I guess they're numbers. There's going to be 15 numbers. Add the 2 cases up. You could have chosen your first restriction and done start with a 3, start with a 4, start with a 5. Or you could have chosen your first one and said start with a 4, and then second one start with a 3 or a 5, because the 3 or a 5 act the same way. And you can put your cases together in more than one way. So the second place that a case question comes up is when you have more than one restriction and your more than one restriction overlap. And then a case question that I always like to do looks like this. Either say greater than or less than. We're still using the numbers 1, 2, 3, 4, 5. And technically there's restrictions on all 3 digits, but only sometimes. Like if you start with a 2, there's a restriction on the second number. It can only be a 3, 4, or 5. But if you go 2 and then 3, then there's also a restriction that the last one can't be a 1. So we have issues only when we start with a 2, right? If you started with a 3, a 4, or a 5, the 300s, the 400s, the 500s, doesn't matter what you put after that, it's going to be greater than 232. So what do? I like to set these ones up by starting off with what would guarantee that it's bigger than 232. If I had my first digit a 3, a 4, or a 5, 3 decisions. If this first digit here is a 3, a 4, or a 5, that means I'm going to count numbers in the 300s, in the 400s, and in the 500s. And doesn't matter which number I pick in the 300s, 400s, 500s, it will be bigger than 232. So by starting with a 3, 4, 5, 3 choices there, there's going to be no restrictions after this. How many numbers are left? 4. How many numbers are left? 3. For 36. What were we avoiding? We were avoiding the problem. The problem was when you start with a 2. So that's going to be case 2. So if I start with a 2, I now have restrictions on the second digit. And now the second digit could be a problem if it was a 3. So what I like to do is I like to say, okay, now I'm going to start with a 2. Then what would guarantee me that it was bigger? If after the 2, I did a 4 or a 5. So if this second digit was a 4 or a 5, that would count all the numbers in the 240s and 250s. Guaranteed, if I have 240s and 250s, they're going to be bigger than 232. So I have one choice here, 2 choices here. I've used up 2 of my numbers. There's no restrictions here because I'm counting in the 240s and 250s. 3 numbers left for 6 choices. Have I counted everything? No. I have to do a case 3 now. I haven't counted starting with the 2, then a 3, and counting numbers in the 230s. What choices do I have for the last one? Is there restrictions on the last one? Yes. So whenever there's restrictions, we need to write the numbers underneath to show those restrictions. Because if you just try to do this in your head and you say to yourself, oh, numbers bigger than the 2 could be 3, 4, 5, and put 3 in there. Why is the 3 in this last space going to be a problem? You can't actually choose the 3 because the 3 is already used up. You see, the only choices in the end are 4 or 5. For 2 choices, add these up. Two plus 6 plus 36, 44 numbers. So you'll see some of these on your take-home quiz. I always put one on your test as well. When you're asked to say how many numbers are greater than something, I always started off with what would guarantee that it's greater. If you started with a 3, 4, or 5, you're in the 300s, 400s, 500s, you're going to be guaranteed bigger. That's case 1. Case 2 says, okay, what haven't I counted is the numbers in the 200s. Is there restrictions on my second number? If there is, What would guarantee that it's greater? If my second restriction was a 4 or a 5. Because then I'm counting 240s, 250s. Guaranteed bigger than 232. Have I missed something? Yes, I haven't counted numbers in the 230s. So I start off with what would guarantee you is biggest with that first number. Then add the 2 and then look at the second digit. Do I have to deal with that? Sometimes you do, sometimes you don't. Sometimes you can get it done in 2 cases. So the cases strategy comes up whenever you can't count something correctly. Then you have to break things up and work together. All right, so stop the video here.